They also see exactly what we see. Just let's hold on. Just want to see. Yeah, and it is going to pick up. I'm waiting for the YouTube to respond. Come on, come on, come on, come on, come on. Yeah, it responded. Therefore, I'm gonna go back. Yeah, great. Therefore, today, my plan is to go through this PHYV tutorial 8, question number 1 to all the way to question number 8. Because you guys, you wrote test yesterday, James didn't get time to go through, therefore I'll be going to at least up to question number 8, or the fluid dynamics. This thing is to do with liquid fluid, and I'm going up. It's to do with the fluid mechanics and the wave. Harold will take you for the wave tomorrow from question number 12 on. Therefore, we will be going with question number 1, which is to do with fluid dynamics. I'll be happy if you guys involve also. Let me record the habitation in case these kids want it. Let me start recording, and I don't know, I forgot even where is this record. Forgot record. Yeah, good. Start recording. The recording will start soon. Okay, that's done. No worries. Therefore, let's go for it. Question number 1. As usual, I don't have today the luxury of the PowerPoint. Therefore, I'm gonna use my tablet to work through. Guys, if you have questions, those of you especially on the Teams, you can just switch on your mic and ask me a question. Those of you on the YouTube, because I'm not following up in terms of voice on the YouTube, please send me a chat. I'll see you directly if you have any question over there. Being said, let's continue. Therefore, those of you on Teams, I'm not following up the chat. Please just raise your hand, or don't raise your hand even I may not see. Just switch on your mic, continue speaking. Don't worry about interruption. I'll be happy if you interrupt me even. Okay, being said, and I'm not following up. You could see I'm minimizing all the Teams, therefore I can't see what's happening until you speak out. Question number 1. It says it's a blim is filled. It's some sort of helium. I believe it is kind of a helium balloon, which is filled with 200 meter cube of helium. You could see that the volume of the helium inside that balloon is 200 meter cube in SI unit. Good. And then the question asks, how much mass can the balloon lift? Okay, remember now we're talking about fluid. Therefore, we have to think of about the buoyancy force. Buoyancy, I don't know how to pronounce in your way. Buoyancy force, that B. We are basically dealing with that sort of it. It says what is the weight or the mass this sort of helium balloon can lift if the volume of the helium is 200 meter cube. That's all what we know of. And then it's given, the next is the density of helium is 1/7 of that of air. And then the density of air itself is 1/800 of that of water. To answer everything up there, you have to know the density of water first of all. I hope by now you know that the density of water in SI unit in kilogram per meter cube is 1,000 kilogram per meter cube. I'm gonna bring it in and just keep an eye. I'm gonna write here the volume V naught. You can't see what I'm writing now. I'm copying 200 meter cube, and then density of the helium, rho of the helium Hg, He is 1/7 of air, 1/7 of density of the air, and then it says density of the air itself is 1/800 of that of water, density of the water, WATR. Now I'll display what I'm talking, and this is, you could see my handwriting. Habitations, can you confirm it to me? Can you see? Obviously yes. Thank you. Therefore, this is a given. What we are looking for is, if you think of this thing is like a balloon, which is given obviously. I'm gonna go red, but right there, and then I want to bring right red. Okay, then if you think of it as a balloon, then filled with helium, that is the volume V naught I'm talking. It must start moving up, but because of the gravity, obviously, gravity, the weight will pull it down. That up is what we call a buoyancy force B. Remember, now with fluid dynamics, Professor Tim and Dr. Lindsay must have taken you through that B, the buoyancy force B, must be equal to, basically, it must overcome the weight. I hope you guys, did you go through? Somebody shout. What do you call about B? What is the equation for that? You agree? This B must be, I don't know if you agree with me, that means the density of the A, density, or somebody coming in? Hey, in town. Somebody's mic is on. I thought you coming to assist me. Sipiwe. Mr. Sipiwe, I'm gonna switch you off then. I don't think Sipiwe is hearing us, but his mic is on. I'm gonna mute him. Yeah, it's muted. Let's go back. Then what I've been saying is, oh, okay, somebody raising hand. Sorry, I just saw when I'm closing. Yeah, Sipiwe. 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 Invitation, is that you speaking? Yeah. Let me connect, let me connect my headset. I can't hear you properly also, Habitation. What did you say? Sorry? Yes, I saw it was Sipue who raised the hand, but when I give a chance, he is not speaking. I thought he looks like he's also in town. I could see the car hooting. That's why I muted him back. Otherwise, let's continue. He will come back, hopefully. Okay, good. Then if I push you now, the buoyancy force, which is pulling this thing up, must overcome the weight of the man. Remember now the question asks, what is the mass that this thing can lift up? If that is the case for me, there is a mass. This is a mass of the weight of the mercury itself, by the way. Mercury, I also have got its weight. Then the other guy, or if we're talking about lifting a mass, let's call lifting a human being, it must have a mass m, or gravity, like mass times gravity. We're looking for what is this mass that this helium with a volume of 200 meter cube can lift up. There is no acceleration involved, but just to lift it up. If you see therefore, for me, I will say the sum of all forces along y must be equal to 0 if there is no acceleration. Basically, this thing is lifting it up. Then I say, then if that is the case, basically what it means is the buoyancy force that this thing is applying minus the weight of the system, the balloon. Let's assume that the balloon is massless or very, very small. Therefore, I will remove the mass of the plastic that is in which the helium is confined. Simply use therefore the helium He, not Hg, by the way, this is He, minus weight of that person, or weight of the mass, must be equal to 0, because the buoyancy force must pull this thing up. Then I could put that B, that buoyancy force minus mass of the helium, He, gravity minus mass, the one we are looking for, times gravity must be equal to 0. I'm looking for M. Now, I was speaking about, do you know how to find this B? That, yeah? No, it's moving with a constant speed. You see, think of it. Can you see what I'm highlighting here on the question? It's lifting it up. It's not accelerating. If it is just picking up and shooting it with a speed, if it has got acceleration, I cannot say equal to 0. But for this thing to happen, the buoyancy force must be greater than the weight of the man and then the weight of the helium itself. It's just moving. It's a lifting up, no acceleration. That's the only thing I'm saying, equal to 0. Okay, then let's put together. What I'm looking for is how do you define the buoyancy force? The buoyancy force is basically, if you go back to your course, therefore B must be the density of the material inside, which in this case the helium, He, times the volume of, which I call it V naught, the volume that you have it. This is exactly the volume. You agree? If you are with me, then I will put this one instead of rho. Remember also, kind of, let me write that one. Yeah, I must reduce this size, man. It's too big. I know also that the density is mass over volume. Then I could see that this implies that the density is okay. Maybe I don't need for now, but keep in mind we might use that formula also. But I'm interested only inside here now. That equation. I'm looking for the mass M. Then if you put together for me, put it up, I'm gonna say therefore volume of this thing which is filled in, the volume is gonna come in terms of that one. I'm gonna put this equation there into the equation, that density of Hg. Am I alright when I'm reading how much can it lift? I'm reading back, is filled with helium. How much mass can the balloon lift? I'm just reading back. The density of helium is given. I only have density. I don't have I have got the volume, and therefore I'm gonna just put that one there. I think I'm alright. I'm gonna just put it there now. I'll put therefore rho of the helium, volume of the helium, or V naught. This is M times the gravity. I'm missing it. This is a force. This is mass. That is gravity. That was what was in my head. Something was wrong. G. I must bring that G minus mass of the helium. Yeah. Something is missing in my head. What is it displacing? I think I know. Something is wrong in my head. I could see. You see, when it is actually moving up, it's a conceptual. When it is moving up, it's actually displacing air, not the mercury. This is a critical. I'm going back to my equation. This B, what is that? That B, just hold on there. This B is wrong. It's not helium. Just hold for me here. I'll go back to it. What I mean is, when it's actually displacing, when this thing is moving up, I'm concentrating here, it actually displaces the air in the surrounding. You see? That the bouncy force is actually to do with the air this thing displaces. It has to be able to push the surrounding air. Therefore, if you put for me there, that B is actually the density of air times the volume of the air, that the volume of it displaces, obviously you could see that it's the volume of the whole balloon. Therefore I could say this one is the volume V naught times the gravity G. Do you agree with me this one? I'm going to stop there because I made a mistake there. The bouncy force, B, is to do with the amount of the air it displaces when it is lifting up. Habitation, you always ask a question, therefore, are you happy with my assumption now? Good, good, thank you. Therefore, let's put it in. Therefore, density of the air, volume V naught, I take the same volume as a helium because this is the same, times gravity minus mass of the helium, He, times gravity minus the m that you're looking for times gravity must be equal to 0. Now you could see that the gravity in principle disappears from everywhere. Then I could say that the density of air V naught minus mass of the helium minus m, or equals to m. If you don't mind, I take that one to the right. I'm looking for m. Yeah? Yeah? Oh, yes. I'm just, of course, you multiply gravity everywhere. It doesn't matter. I removed it basically because it's everywhere. I'm equating to 0. If you continue with the gravity, it doesn't matter. You could get the same answer. Good. Then let's push. Then I will say now m. My m must be equals to density of the air, volume V naught minus, remember the mass of the helium is not given. Therefore, I'm going to say density of the helium times volume of the helium, which is V naught again, because that volume is what is given. This is exactly the amount of the volume that the system displaces. See? Therefore, I'm almost there. Then I say, okay, good. Then V naught is constant. I'll simply see that the density of air minus the density of Hg. Like He, helium, not the mercury. Then I'm setting up my equation nicely. I was given that. I know density of air is given by, I'm going to read it here on my note. The density of the air is 1/800 of that of water. Then I'm given that it's 1/800 of the water. If you don't know that of water, density of water is 1000 kilogram per meter cube in SI unit, or is the same as to 1 gram per centimeter cube. But remember, we are using in SI unit, therefore you should always use the one with the SI unit. Then I will say it's 1000 kilogram per meter cube. Then I will see that this thing is to 0. What is that? 10/8 means 5/4 kilogram per meter cube. I've got that of air. And then again, it's given that the density of the He, the helium, is the equation states that it's 1/7 of air. I will say 1/7 of that of the air. I just calculated that of air, which is 5/4 of kilogram, the unit kilogram per meter cube, which is equals to, maybe I will leave 5/7 times 4 is 28, I believe, 28 kilogram per meter cube. I almost set it up my equation. Then that mass, therefore, the mass equation should be the volume V naught is 200 meter cube. You could see now why I'm stuck on that one. That of air is 5/4 minus that of the helium is 5/28, guys, and then a kilogram per meter cube. You see the meter cube now is happy, chap, and then that one disappeared. Therefore is a 200 into 5/4 minus 25/28. I think I just used the calculator. What is this? Yeah, I'm gonna multiply what is 1000, I think. 5 times 1000 into 28 minus 4/28 times 4. Just somebody put together. I don't have a calculator with me. Somebody say to me, what do you get? Or I'm gonna use my phone. That 28 is 23 divided by and then 300. Are you sure? You say, okay, let me do also. I stopped in between. Yeah, it's okay. Okay, guys, I stopped working. But the answer should be in principle. Iteration, find for me something. Okay. Okay, it looks reasonable. I see 214.28, you say kilogram. Thank you, girl. I didn't see your name, but I know a girl is speaking. AR, yes, yeah, that's correct. Therefore, let's say around 214 kilogram. And then, okay, let's check if we are correct. Click. I'm sure we will be. You should be correct. Check. Hey, yeah, correct. 214. We should be happy. Agree? Let me check if my YouTubers are doing anything or if there is anybody. I don't see anybody. Oh, there are 2 current viewers, guys, on the YouTube. Sorry, I didn't come back and view you. There are only 2 though. Please send me a message. Hi, I'm just gonna chat. And then I'll pop in and out to check what you guys are up to. The teams, you should be happy. We are happy with that one. Basically, what we did, we have a balloon. The balloon must displace air. That displaced air is density of the air, volume of the air times gravity. And then what pulls it down is the helium plus the mass. The helium has got mass times gravity. The man or the human being inside the balloon must have also mass times gravity. You simply equate the buoyancy force must be equals to or greater than, to be specific, greater than the weight of the helium plus the weight of the human or the weight of the mass that it's supposed to lift. Then solve for weight of the mass and then gravity, as I said, you could remove it or work it together. We got it 214.28 kilogram. Happy? You should be. Question number 2. It says, is a boat is floating in a small pond. You can't see what I'm drawing. I'm gonna draw now. I'll display for you. Question number 2 is a boat is floating in a small pond. The boat then sinks, so it is completely submerged. What happened to the level of the pond? Oh, it's just a theory though. I'm not gonna work through this one. There is nothing I could do in principle. What do you guys say? Is a boat is floating first. Now the boat has sink. If it sinks so that it's completely submerged, now everything is under the water. What happened to the level of the pond? Do you think it increases or decreases or it stays the same? Why it decreases? The answer is yes, it is going to decrease. I could convince you that the professor team also said it's going to decrease. Yeah, that's right. What happened though? Why? Okay, good. What about the other ones? Guys, what do you say? Uh, I could see where you're going, but I believe you have got a concept. Let's see like this. It's actually level of the water is like that, and then this small boat is actually at the beginning. She is just floating. Let's say a little bit of it is inside. Yeah, and then the boat now in the second scenario, and if you have got now, think of a pond. This is the level where it was there when it is floating. The question is, it says, what happened if this boat now is completely inside, submerges in, and then it's saying, is this level going to increase or rather is going to decrease? The answer is it's going to decrease. And my assumption is, I think, habitation, you're going to agree with me. What happened is, in this situation, by the way, it's pushing it down. There is a buoyancy force that because the weight of the thing is on top of it. As a result, it must push the water down. When the water is pushed down, it must raise. It must have raised. That's what the initial H naught is. The moment it submerges inside, that buoyancy force is no more there. That means if the level of the water is there now, it is rather is going to come back to below where it is at the beginning. Basically, here you have got the buoyancy force B. Here you don't have anything because it is submerged. Nothing is pushing the water from top down. As a result, the water level is no more increasing, rather it's going to subside. I don't know if it makes sense for you. Yes, it's equal when it was floating, but now it is submerged inside. It is at the beginning, yes. AR, AR, you wanted to say something? Okay, then let me go back. And what I was saying is, when the boat is floating on the top, as you see on the screen, there is a buoyancy force I'm talking about here. Because the buoyancy force here is the density of the water displaced, the volume of the water displaced times gravity. There is a displaced water. That displaced water causes the height or the level to be higher. Now, when the boat submerges in, that buoyancy force no more exists. Therefore, nothing is pushing the water down. If you push the water down, obviously it must raise in some ways because water is incompressible. You can't compress water. The moment you remove that B, the buoyancy force, the force disappears, then there is nothing is pushing it down. Therefore, the level becomes lower than what it is used to be. Makes sense? Okay, thank you. Habitation also, you said, okay, good. I could pick. Let's go back to our calculation. Number 3 is about a hydraulic lift. You guys, you are engineer. You must be thinking of, especially those of in mechanical engineer, you're going to use a lot of time about this hydraulic lift. It says a hydraulic lift raises a 2,000 kilogram automobile when a force of 500 Newton is applied to a small piston. Bernoulli's principle. What is this principle, guys? Remind me. Okay, let me first draw on my here also. I'm gonna. Okay, I'll go back to the question. It basically says there is a hydraulic press. One side is a small area, the other side is a big area, and then it says the small area of the thing is if the small piston has an area of 10 centimeters square, I'm going to call this one A1. A1 is equals to 10 centimeters square, and a hydraulic lifter lifts this much automobile on the bigger area. Obviously there is, don't worry, you don't see what I'm plotting, but you'll see soon what I'm up to. This is the automobile. I'll make my ugly car like this, and that means it's gonna lift up this one. Let's call this one F2, and then it has got area A2. Then the question is hydraulic lifts are this weight when this much is applied on the smaller piston. Okay, this one F1 is 500 Newton, and then what is the cross-sectional area of the larger piston? This is what it looks like, the one I was drawing. And this is basically how your brake system also works, hydraulic press. Think of you filled up this thing with the fluid, with some sort of either brake fluid or any fluid that you could think of it. In a car, it's actually oil. Then you have got a piston. This is the area of the piston. This is also how you press your brake. If you apply 500 Newton, it says, on this smaller area, you could lift up this automobile where the weight of this car, weight of the automobile, I'm going to go AM, is 2,000 times the gravity G. That's the weight. You would have this much. And then the question he asks is, what sort of area is A2? And then you need one main concept here. A pressure inside a fluid is the same everywhere. If we call this area has got a pressure P1, and then that area has got a pressure P2, inside this fluid, P1 is equals to P2. What is this principle called? Is it Bernoulli's? The question is basically the pressure inside a fluid is the same everywhere. I forgot the name, but you could just, this is a concept you need. P1 is equal to P2, and then you go back to your physics. But we know that the pressure P is force over area. That means this implies that the P1 is equals to F1 over A1, and then P2 must be equals to F2 over A2. Because they are the same, I could simply put together that the F1 over A1 must be equals to F2 over A2. Then I basically solve for A2. A2 equals to, I'm just recrossing, F2 by F1 times A1. Pascal's principle, Bernoulli's principle. Pascal, I believe, yes. I forgot, but let's go check. Pascal's, I believe. Pascal's principle. My spelling is go a long time ago. Pascal's. It's gonna bring for me the worry principle. Principles. Is it Pascal's principle? Exactly the same. You see, even the question must have been copied from here. It's a Pascal's principle. Thank you, Habitations. You see, it says P1, which is, or pressure 1 here, P1 A1 must be equal to P2 A2, or force 1 is equal to, no, pressure 1 is equal to pressure 2. It's a Pascal's principle. Thank you. Let me go back to my work. Therefore, we know where we are up to. A2 must be, F2 is that 2000 times the gravity, I don't know what they're going to use, 9.8 divided by F1 is given 500, and therefore times, in terms of centimeter, is going to be times 10 in centimeter square. What do you get? I'm waiting because okay, maybe I'll simplify a bit. This go by that, this go by this, therefore it's a 200 times 9.8 divided by 5. Then instead this one by 5, 1 by 5 is 4. It's a 40 times 9.8. I don't know what you guys say. 4 times 10 is 400. It should be close to 400. Let's say, I don't know. You guys tell me. Yeah, I agree. You see, it's close to 400. I simply say 392. Thank you. And the answer should be that one. And check, it should be the case. Come. Yeah, 392. Happy. Basically, the Pascal's principle. Just reminded that this is a Pascal's principle. The pressure inside a fluid is the same everywhere. If the pressure is the same, that means force over area is the same everywhere. If you've got A1 and A2 is F1 and F2, you can recross and work whatever is missing. Good. Oh, I forgot my YouTubers. Is anyone still there? Oh, thank you for the like, at least 3. And you see now my internet is not going well. Sorry for the YouTubers. It's a connection from the internet. But who is Mardi? Mared is decreases. Thank you. Mared is with us. Mared, sorry, man. Man, I call it a man or a girl, I don't know. But he was discussing with us and I forgot to check my YouTube. But anyways, happy that somebody is at least following on the YouTube also. Let's go question number 4. What did I say? What is this up to? It says all people come very close to being able to float in the water. Not me. I'm like a rock. I will fall in. I don't know how to swim. But this one says all people come to very close to being able to float in water. Okay, maybe I don't know the technique. What force? Therefore, it says what? Therefore is the volume in cubic meter of a 50 kilogram woman. We want to know what is the volume of a woman. Easy, man. Length times width. Length of the woman times cylinder base area times height. I'm teasing. We don't go that way. But we want to use the principle of Bernoulli's principle. Now I remember that is a bouncy force. If this lady able to float on top of the water, let me again. Now you could see what I'm doing, and let's say this is a level, and then this nice looking girl or a woman is floating, but some of her body is actually underwater. Yeah, she's good in swimming like a fish. I'm teasing. Like that. Therefore, this one actually, the bouncy force B must be equals to the weight of the woman, W of W. That small w is that of woman. This must be the case, otherwise she will sink. Then, with this assumption, the only thing left is what is B. We know that this one is mass of the woman times gravity. But I should be aware that the buoyancy force B is actually whatever is displaced. You see, when you fall inside the water, you displace the water. Then I will say weight of water, W-A-T-E-R, displaced, meaning you displace this water, times the gravity. And then I could see that this thing should be the weight of weight displaced water. I could say, it should be density of the water, W-A-T-E-R, because the woman also is W, times volume of the water displaced times gravity. But if you see now where I'm going, I believe that is a correct way to go. This volume of the water displaced is the same as to the volume of the lady. You agree? You should be. That's all what is displaced. That volume of water displaced is the volume of the woman because she is just floating. Isn't it? Being able to float, yeah? Therefore, what the volume, that's where we're going. Go back to it. Therefore, I could put this one, then this is density of the water, volume of the woman, W is woman now, times gravity. This must able to balance that one. Yeah, and what else I need? I think that's all. Then if I say so, volume of the woman from this equation, I'm bringing up, volume of the W-O-M-E-N, this is the same as to W-O-M-E-N. I'm talking about that volume. It should be the bouncy force divided by density of the water times gravity is under, because I'm taking this times this on the other side, then which I will say equals to the weight of the woman or mass of the woman, gravity over density of the water times gravity. The gravity will cancel again. If you don't want it, keep it. Therefore, it's equal to mass of the woman divided by density of the water. This is a correct answer. And that is how big is she? 50 kilogram divided by the density of water is, I said to you, 1000 kilogram per meter cube. Then you could simply see that this must be equals to tam-tam, and that will go. Therefore, 0.05 meter cube. That's what I say. What about you? 0.05. That's what I say. Yeah, you guys, you happy? Invitation? Yeah, thumb up. Thank you. Yeah, good. And I believe these things just basically assumption. Yeah, good. Let's go here. Question number 5. We have long way to go. I want to go all the way to question number 11. Question number 5. Yep. And let's read thoroughly. By the way, I didn't see these questions, but I know these ones are from last year. And I've been setting up them, therefore I remember what the questions, but I don't have in my head already. It says an empty spice bottle has an inner volume of, okay, I'm gonna, as I read, I'm gonna take it onto my tablet. This is question number 5. An empty spice bottle has an inner volume of, let me call it V in, the inner volume of 1.31 times 10 raised to minus 4 meter cube. This is a volume. It has a mass of what is that? Let me call it bottle, capital B. It has got 112 gram. I always write in kilogram, 0.112 kilogram in SI unit, so that I don't forget about the SI unit. And then it has displaced, okay, what did it displace? Water. Okay, density of, or volume of V of, right man, V of the water, this WD, I'm copying it. You will see 1.63 times 10 raised to minus 4 meter cube. When fully submerged, meaning that when it fully submerged, you get this one. Now, what the volume of mercury, density of the mercury, Hg, is given, which is 13.6, we know this one, times 10 raised to 3. By the way, mercury is very dense, kilogram per meter cube. You can see it is 13.6 thousand, you see, kilo. 1,000 kilogram per meter cube must be added to empty the bottle so that it will just submerge. Now, if you replace the air with mercury, what is the volume of the mercury required to just submerge it? And I could bring my tablet now out. This is what I've been copying. The volume, inside volume of the container. You could say this one is also V0, let me call it. The inside of the container is this much. The weight is that much, not weight, the mass, 0.112 kilogram. Weight, volume displaced for water, WD, this is what I'm talking. WD there is 1.63 times 10 raised to minus 4 meter cube. Now a mercury is replaced where the density is given. We're looking, what is the volume of the Hg? Any hint? What you would have done? Or should I just push? By the way, I don't expect you that you have gone through, because you guys, you just wrote yesterday also another test, and maybe you didn't have time to look through. This is what I would have done. What I'm going to go is, as usual, at the beginning when there is air, I could think of like this. I'm going to make like this, okay, and then there should be some sort of hole. Let me make like this, and this is a container, and then there is a hole. I know I'm going to collect this displaced water. That's my thinking. Then when I printed this question paper, I'm going to read from the question paper I just printed. It says, an empty spice bottle has an inner volume of this much, and when fully submerged, you know. Therefore, when you put this container inside this one, let me put this one as a container, and filled with air, and there is a water here. This is a water. Then the water, let me make this guy a little bit up, taller, so that you could see. The water come out, and then I know I'm going to collect it here, and then the water fill up here. This is a volume of water displaced, which is that much. And then the air inside this container, let me use it like a, okay, let me put water like solid, water like air, fully, when it is fully filled up, this is the water, therefore that's the volume you got. Inside here, the dot 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 is the volume of that thing, that volume in. Now the question is, you want to fill up this thing with mercury. Remove the, now bring a mercury in. Let me make a very small syringe in red. You bringing a mercury. Oh, I didn't change a pen. Come on, change that. Okay. And I'm gonna bring mercury in, and then I'm gonna inject mercury inside here. As I inject, the mercury is gonna displace the water, the air, obvious. Then it asks, what is this volume of the Hg that you need to apply so that it says it must be added to empty the bottle so that it is just submerged. It's not going to be full like air. The volume of the mercury must be obviously smaller than the volume of the air or the volume of overall. I could think because the mercury is denser. It is heavier basically. Therefore, I'm looking for what is the volume. That makes sense for you? Then with this agreement, I'm going to continue. Then I will say, at that instant, basically when it is with air, remember, we have got down, which is all the weight, let me say W all, and then when there is a buoyancy, must balance the buoyancy. This is a case. With this standing point, I could see simply that B must be equal to W, all the weight added. That of the air, that of the container itself. Okay? Then I could, now when it is replaced with mercury, when the air is replaced with mercury, I could write this one as equals to this. Now mercury is added, the glass is there, mass of the beaker, plus mass of the mercury Hg, because both of them has got gravity, I will say equal times G. When the mercury replaces the air. I'm holding in case you might say, what are you up to? But that WB, that buoyancy, I will get from the given condition. When it was filled with air in the first place, and then this thing is filled with air and it still is fully immersed inside. You see, filled in air is completely filled in and then displace the water. I could see that that beta must be equal to the weight of the water it displaces. Because remember, that is what is given here. It displaces a certain amount of water. I will say weight W of water displaced. If you have that concept, then I could write that one as density of the water, volume of water displaced times the gravity. You see where I'm going? On that pen. What I'm going is, I've got this one, and then I've got that one on the side. These two equations must be the same. When it is filled with air and then displacing water, now it is filled with mercury. It's going to displace a certain amount of water, but that water, we don't know what that volume is. That volume is actually equal to the volume of the mercury. If I equate these two equations, therefore, I'm going to put it here. Density of the water, volume of water displaced, which we have, times the gravity G must be equals to, what equation I have there? Okay, mass of the beaker, which is given, plus mass of the air, but the mass of the air at that time should be very small, plus mass of the mercury Hg times the gravity. I put my equation now together. Then if you agree, or if you keep it, but I don't like to work with the same variables on both sides. I'm going to remove my G from both. Then I will say my equation is logged here, which equals to mass of the beaker plus, instead of density of the mercury, I could say, instead of mass of the mercury, I will say density of Hg, volume of Hg. You see, that is what I'm up to. That's what is a noun. Then I'll bring therefore, density of the mercury Hg, volume of the mercury Hg I'm looking at must be equal to density of the water, volume of water displaced, minus mass of the beaker B. Maybe one good assumption you should take that this mass, I'm coming back, this mass is mass of the air plus mass of the beaker, but you could know that the mass of the air is incomparable with the mass of the beaker. This is a heavy mass. 112 gram is not easy mass. Therefore, I'm just assume that mass MB is what is given. Then if I solve now for the volume of Hg, must be equal to 1 over density of the Hg, which is given, into the density of water, it's 1000. Volume of the water displaced, what is the value? 1.63. 1.63 times 10 raised to minus 3 minus the mass, which is 0.112 in kilogram, and therefore this one is 1 over 13.6 times 10 raised to 3. Remember, this is a number there. I'm writing small now. I'm going to pull this way. That one will the 1000, believe me, this will remove. Therefore 1.63 minus 0.112, I believe that will cancel. And then if you put together, I don't know, give me a value, what do you get? I think it's very close. Why don't I use Excel? Yeah, somebody? Everything. You saying if I just repeat 13? Or 1 over 13.6, but did you do this minusing? What is the multiple choice says? Can you make it in centimeter cube? Why? Maybe. Wait. I see something. Habitation. Hold on. You see? I'm coming back. This is actually 10 raised to minus 4. Check there. The one I'm highlighting. You there? Therefore, hold on. There was a little bit of actually it's just a number. When I make this one, this is not minus 3. This is actually minus 4. Come on, minus 4. That is, let me use a different pen. I made a mistake. That is minus 4. Therefore, it's not 1.63. It's actually 0.163. You can't see what I'm writing. That is 10 raised to minus 4. That means 0.163. Let's do together. 3 minus 2 is 1. 0.1. 6 minus 1 is 5, 1 minus 1 is 0, 0 point, I'll simplify for you now, 0.051. Did I say 51? Yeah. Now this thing is should be in meter cube. Therefore, I'm gonna put up. Why don't I use Excel instead of calculator? Of course, you could see what I'm doing there. Come on, Excel is coming. What I mean is, I'm supposed to say, okay, equals to, can you see what I'm doing? Plus, 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 okay. Make this number 48 equals to 0.051 divided by 13.6. What do I get? Yes, you see, you guys were supposed to give me this one, 0.00375 meter cube, but I know, correct? Yeah, good, great. Then let's make it 1 meter cube. 1 meter is 100 centimeter. Therefore, 1 meter cube is 10 raised to 6 centimeter cube. You agree? Oh, you can't see now what I'm writing. 1 meter cube is 100 centimeter. 1 meter cube should be 10 raised to 6 centimeter cube. Therefore, I must multiply this one by 10 raised to 6. 1, 2, 3, 4, 5, 6. Do you think even we have an answer there? Anyways, by the way, it should be around, if I guess, maybe the number is not correct. I could see this should be the correct answer. Let's see. Yeah, it should be 3.75. I don't know if we made any mistake on the number insertion, but this is a correct one. Becky? Yes, you see the volume of the water displaced is also that much. That's where I made a mistake. I write through, but you could see up to here is correct. This equation is correct. What I mean is this equation is correct. Just replace the given values properly. Let's push forward. What is question number 6 waiting for us? A super tanker filled with an oil has a total mass of this much, 6.1 times 10 raised to 8 kilogram. If the dimension of the ship are those of a rectangular box of 300 meter long, 80 meter wide and 40 meter high, determine how far the bottom of the ship is below the sea if the density of the sea is given by this. Basically, I think this is straightforward also. What I'm going to put is, okay, there is a sea, of course it's a rough sea. Then I'm going to have a ship, a super ship in the form of rectangular box, kind of such a thing. Therefore, if it is such the case, it should be kind of a cubic, I'm guessing, but it may not be a cubic. And then like this, it has got a length, it says length L, this much, a height H, this much, and then a width W, that much. Then obviously this is the geometry of what is given, but we know of that this is a sea. Some amount of the ship is inside the sea. This is the height H naught we're looking for. What is the height this thing is immersed in? And then we have to use obviously our principle. The buoyancy force must be equal to the weight of the ship, let me call it SH. The ship. It's not a ship, bad ship, the animal ship, this boat ship. Okay, if that equation is the case, therefore the buoyancy force is going to be, remember now we're looking into it, the boundary force beta, or this one should be the weight of displaced fluid, or in this case C. Therefore I will say density of mass of the, okay, let's push how far we go. What are you looking for? I think I'm tired. What are you looking for? I'm gonna go back. We know the mass, super tanker with the oil has the total mass. The mass is given. If the dimension is given, oh, by the way, the volume, three-dimensional object, volume of the ship is going to be, or the tank, should I use it tank or SHIP? Don't worry, SHIP is length times width times height. This is overall volume. You can't see what I'm writing again. That's a volume. Therefore, I could simply see that this must be the same. They must balance. If that is the case, just put together this number. What do you get? I get. Come on. See, I'm getting tired already. I will say mass times gravity must be equals to density of the sea, or the sea displaced. Instead, because I don't know mass, I will use density times volume. Density of sea, volume of the sea displaced, I must say this one, times gravity, where this one is a mass of the super tank. Again, I'll remove my G on both sides. That M must be density of the sea. Remember that this is a very conceptual now. You have to interpret that. The volume of the sea which is displaced, the volume of the sea which is displaced is equals to the volume of the ship which is inside the water. You agree? The volume of the sea displaced is equals to the volume of the ship which is inside the water. If that is the case, I'm going to just draw here. Think of it, it's just side view. Assume it's only up to here that this thing is inside the sea. It's not the whole height h, but a small height is what? Inside the sea. Therefore, I'm going to call that h naught. I'll simply say that the length of the ship times the width of the ship times the height h naught, where that h naught is actually what we are looking at. How deep from the bottom of the ship, how far this thing is inside the sea. Habitation, you are my springboard. Do you agree with what I'm saying? Okay, good. If you ask me, I have you at least. Oh, I forgot again. YouTubers. Oh, YouTubers, you guys, there is a warning, but you see, it's only one person watching. And most of the time, I'm losing these people. Okay, let's go back. And I'm looking for h, which I'm in question. Then I'll simply say that h naught, which is the height of the ship, which is inside the sea, must be equal to the mass, which is given, divided by density of the sea times length of the ship times the width of the ship, which we say now, based on the given equation, it says, you can't see what I'm writing, 6.1 times 10 raised to 8 in kilogram, divided by the density of the sea is 1020 in SI unit, times the length is 300, times the width is 80. We must get our h less than 40. The overall length of the ship is 40. We must get less than that. Come in. Let me first display to you. This is what I had. 10 is there. And I want to change a pen just to simplify a bit. There is 1020. I'm going to make this one raised to 6. Therefore, I'm going to go back to my Excel rather than that one. I'm going to say now I've got 10 raised to 6 equals to 6.1, 6.1 divided by 102, which I'm gonna go back. Don't worry, you see what I'm doing, because I don't have a calculator. 102 times, what else I have? I would have removed 20 there. Instead of 6, I'm gonna have 4 times 2, no, times 8 rather, times 3 times 8. I'll show you what I'm doing. And then raised to 4. 1, 2, 3, 4. It's 24.9. I'll get 24.9 in meter, around there. Let's see. I'll show you what I'm writing. This is what I did. You see, there is 300 also here. 1, 2, 3, 4 already. Therefore, that's the exponent becomes 4 instead of 8. I divide that one, I get 24.9. Let's go back to our answer. Hey, there is no close. Maybe 25. They are not that much accurate like us. You agree? I'm gonna say 25. Check. Hopefully. Yeah, 25 is correct. And of course, you could see that it's less than 40. The overall of the ship is 40. What is immersed inside the sea is 25 meters. Happy? Let me see my YouTubers. Only one people watching. I don't know if that person is still there. Okay, number 7. It says a wooden block is placed on top of an ice. Let me start drawing what it's saying. Question number 7. It's a wooden block on top of an ice in a large bowl half filled with ice. Oh, okay. This is my stuff. It's half filled with ice. This is ice. I'm supposed to use the blue. This is ice, and then you have got, and don't get, a block. Let me call this one as my block. And then it says the ball is then filled with the brim to the top with the water, with a wooden block riding on top of the ice. As the ice melt, this is, by the way, it's a word problem. As the ice melt, does the density of the water decrease? Of course, you can't play with the density. Density is a given quantity, you can't change. The water level falls below the rim. The water level rises and they spill out of the bowl. The water level does not change. The wooden block descends, causing water to spill out of the bowl. I think this is just confusing. A wooden block is placed on top of an ice in a large bowl, half filled with ice. This is what I've plotted like that. Half filled. And the sitting. Now if you pour water inside here, obviously the water is gonna to the brim, it says there, and then the block is gonna, ice is gonna be, this side is ice now. Let me move it. Red is ice now, and then the block is gonna be sitting there. This is my block. If this ice melt, if the ice melt, what happened is the question. If the ice melt, do you think the water level rises and spill out of the bowl? Is this could be your answer? Do you think the water level falls below the rim now? Does it decrease? Or the water level does not change? This should be the 3 competitive. The first one is wrong. The wooden block descends, meaning causing the water to spill out. No, that's not true. Unless this thing is a wooden block, of course it's gonna float. Let's not bother A and the E. Is it gonna be B, C, or D? And remember, also when you are talking about this one, those of you or maybe you listening to our conversation on YouTube, once it is uploaded, you have to think that as ice melt, when the ice melt, Does the volume increase or decrease? Or let me rephrase my question. When a water changes from liquid to solid, does the density decrease or increase? When a water, like a water, glass of water, when it is cooled down and then freezes, does the volume, the density increase or decrease? Basically, the other question is, if you compare the density of water and the density of ice, both of them are the same material. One is solid, the other one is liquid. The density of liquid water or the density of ice, which is bigger? What should be your answer? And let me confuse you more. Remember, when things cool down, they become so compact, the density must increase. Are you going to say therefore for water also, when the water cools down and then it forms a solid like ice, the density increases? Your answer should be no. Water is a special material. The density of the water actually is larger when it is fluid, and then when it become now solid, the density actually decreases. That is why ice float on a sea. If ice was heavier than the water, the ice would sink. But have you ever seen ice sinking? No. This is a special. Other material other than water, when they cool down, they actually sink. Water is a special case. Therefore, when the ice melt, the density decrease. Decrease in density means mass over volume. The volume must be bigger. If you think that way, it looks like the water level is going to be increasing. But if you think of what is written here, it's insignificant compared to what is there. I believe with this assumption that the wooden block is placed on top of that half filled with ice. The bowl is now filled with the brim to water. When the ice melts, the change in the volume of the overall water because of the melting of ice does not bring that much because it is so small. However, if you're comparing the density of water and density of ice, careful, ice has got less density. Means ice takes more volume than normal water. Do me a favor, do yourself an experiment. Take your bottle, water bottle. Oh, I have it nicely here. You can't see me, those of you on the Teams, but just take your water bottle, fill it to the top, cover it up, and put it in the deep freezer. You will see that your water bottle will explode. Why? When you add the water into the plastic and fill to the top, and then it has occupied a volume or a space. The space it is occupied is exactly the volume of your container. When you cool it down, it actually expands. It's opposite of other things. When water cools down, it expands. Therefore, your water bottle actually explodes, indicating that the volume of a water in a container or the volume of a water is greater than the volume of ice. Opposite, density of ice is less than density of water. However, it is insignificant. According to this equation, it must be, we don't see that much change. I believe D should be the correct answer. Hopefully, Prof. Team also agree with me. Yeah, that should be the correct answer. Maybe I should push a little bit now. I'm a little bit behind. I still have 3 questions to finish. 1, 2, 3, 4 rather. Yeah. Number 8, maybe it is either. As I go on, I believe it should be getting either and either. Number 8 says, find the average density of a red giant star with the mass of R. This thing is easy. what is it? Find the average density of a red giant star with a mass is given approximately 10 solar masses. Okay, I don't care. And the radius is known, equal to radius of T105 times 10 raised to 8 9 meter, equal to the distance from Earth from the sun. Okay, I don't mind. Therefore, for you is you can see now mass is given 20 times 10 raised to 30 kg. Radius is given, it is 150 times 10 raised to 9 meter. Therefore, the question is, what is, find the average density. Basically, this is a basic definition. Density is equals to mass over volume. If it is this thing looks like, I believe you could agree with me, and it's spherical. It's like a ball. If it is the case, then volume should be 4 over 3 pi r cube. This is a volume of a sphere. I believe that should be the way. Therefore, my density must be 20 times 10 raised to 30 divided by 4 over 3 pi is 3.14 times 10 raised to 9 times 150. You put guys together and you should get a correct answer with this one. If I guess, therefore 10 raised to 30, this will take, I'm just going to simplify a bit. 20 times 3 divided by 150 times 4 times 3.14 times 10 raised to 30 minus 9. You just put this thing together. I believe I'm just gonna guess. Difficult to guess. Repetition. Are you sitting with a calculator? Let's do. If you am not gonna make a mistake, 20 times 3 top one, and then the bottom one is gonna be 150 50 times 4 times 3.14. And then it's around the 3 point I know now it's the number is 318 if I didn't make any mistake. 318 should be there. Sure. I don't have that. I must have made a mistake again. Help me. Ha! You laugh at me. I made a mistake. You see pi r cube. You know why? Pi r cube. My pi 4 over 3 pi, not r. This must be cubed. You agree, repetition? Pi r cube. Yeah, you see. Therefore, always when you rush, you make a mistake. Therefore, I'm gonna write. That's okay. 4 over 4 times who else I have? Pi is 3.14, and then the other one is 150 cube. 150 times 150 times 150. This is the problem, is I don't have times 10 raised to 27. This one is 10 raised to 30. Therefore, the 10 raised to 27 is under. Then do it yourself now. 20 times 30 divided by 4 times 3.14 times 150 3 times 10 raised to only 3. I could go back to my Excel. This answer is 150 is actually raised to 3. You see, 1.41. The answer should be around 1.41. There are two 1.141 now. One is here, one is there. Which one is correct? Should be with a negative. It can't be. -4, -3. And what did I get here? This one I must multiply by 1000. This one equals to this one times 1000. Therefore the answer is actually the one, 2, 3. Should be the one with 3. You guys do this one by yourself. This should be the correct answer. E should be the correct answer. Check. Yeah, E should be the correct answer. Hopefully you will pick it up. Again, this year I forgot to edit this thing. You know that this question is copied from America. It says find the pressure in atmosphere in the water at the base of this dam. You could take our own dam. It doesn't matter though. If the water in the reservoir is 200 meters deep. Let me plot this one. It says this is the dam. Let me make it like this. I'm plotting my diagram. Don't worry what I'm talking. There is a water. That height is 200. And then 1 ATM is given. 1 ATM is 1.01 times 10 raised to 5 Newton per meter square. And then we want is what is the pressure at the bottom. Okay, now I could display. This is what it says. You have a dam which is filled to a 200 meter, and then you wanted to find what is the pressure at the bottom down here. Easy. The pressure here, pressure P must be rho GH. Rho, the density of the water, the gravity times the height. But remember, you should not forget also, there is an air pushing this thing down. There is 1 ATM actually here because of the air. The air is pressing down on a water in the dam. Therefore, the overall P total should be 1 ATM plus rho GH, where that rho GH is because of the weight of the water. Then if we put this one together, this should be 1 plus, let me keep that one. Let's first measure the rho GH. Rho GH must be equals to the density of the water, which is 1000 kilogram per meter cube, times the gravity, which is 9.8, times the height, which is 200 meter. But this one is this is Newton per, what is that? Acceleration due to gravity is meter per second square. If you calculate this one, what do you get? 98. Let me go back to it because you guys, you don't help me. I'm gonna make equals to 1000 times 9.8. 9 times 8. 9.8 times 200. This is about, I'm gonna make it big so that you could see. Is what I get here is 1961234 Newton per meter square. Check this one. This is a pressure is Newton per meter square. I'm writing it here. Convert that, it says 1 ATM is 1.01 times 10 raised to 5 Newton per meter square. Therefore, if I put this one also 1, 2, 3, 4, 5, 19.6 times 10 raised to 5 Newton per meter square is how much in ATM. Therefore, that the pressure should be, this is my X. Therefore, rho GH must be equals to 19.6 ATM. You could see straightforward. Therefore, if it is 19.6, I've got 1 from top. The overall rho total, not rho, pressure total, P total must be 19.6 plus 1, which is about 20.6 ATM. I will say that should be the closest I could go. Hey, where is that? I don't know why I get 0.6. I believe A should be the correct answer. Habitation? What do you say? Did I make a mistake again? I'm going back. I know it is 180 m is that much. Rho GH is what I have. 1000 times 9.8 times 200. I go back and check. What did I do? Yeah, 1009.8 times 200. I get this much. Even if I put it in exponent, I could see format cell number, not scientific rather, is a 1.96 10 raised to minus 6 or 19.6 10 raised to 5. Therefore my calculation is 0.6. All right, I say 20.6, even though the closest multiple choice I have is 20.4. Check. It's correct. Habitation, you agree with me? Good. At least I have you. Happy. Question number 10. Oh, almost there. Two more questions. Question number 10 asks, what's that? Some species of whales, species, not a spice. Some species of whales and animal whales can dive to a depth of 1 kilometer, 1000 meters. What is the total pressure they experience at a depth of 1000 with the density of the sea is given? It's the same as that of the very first question we just solved it. Therefore, the total pressure, P total must be 180 m plus rho GH again. But rho GH must be density of the sea, not the normal water. The gravity times 1000. Remember, it is a 1 kilometer is 1000 meter. Then if you put what's the density of the thing given, 1020 kilogram per meter cube. Therefore, you simply say 1020 times 9.8 times 1000 divided by 10 raised to 5 in ATM. I know when you finish, this one is in Newton per meter square, you convert into ATM. Therefore, what do I get? Let me now replace that one. Instead of 1000, 1020. 20. And then instead of 2000, I'm going to go to 1000. What I get? Okay, 10. Because this is 10 raised to 5. Therefore, divided by this, I've got 100. 101. Do you see anything that says 101? ATM, about 1000 kilometers is 1000 ATM. Let me check the question. 101. Which was one? This one? Habitation? Check. Let's go. Yeah, it's about, the correct answer is 101 in principle, but 100 is not bad. Good. Number 11, it says, the pressure inside a commercial airline is maintained at 180 m. I'm gonna go back to my, just to plot, but I'll go back to the question. The pressure inside the commercial airline is maintained at 180 m. Inside pressure is, P inside is 180 m, atmospheric pressure. What is the outward force exerted on 1/2 meter cabin door if the outside pressure is 0.3 atm? P outside is 0.3 atm, meaning now it looks like it's a cabin door. Obviously, it's a door. It has got 2 meter by 1 meter. I'll bring it now. What I've been talking. This is what it looks like. If this is a inside, I'm going to use red pen. From inside, the pressure is P1. From outside, the pressure is P out. They push each other. For this thing to be at equilibrium, this the delta P. What is the question in principle? It says, what is the outward force? The force. Force, I'm gonna go like this then. Pressure, delta P rather, delta P is force over area. You agree? Meaning P in, P out. It's not balanced. Delta P must be force over area. Then I will say the force must be the area times the delta P. Therefore, delta P is, this one is 1, that one is out. Basically, 1 minus 0.3, 0.7 ATM, obvious, in ATM. Area is 1 meter by 2 meter. I'm going to just say 2. 2 times 1 is 2 in meter square. Then the answer is supposed to be 0.14. No? 1.4. Oh, okay. Let me just hold on. What is the question all about? Let me hold here. Oh, I'm guessing. It's in Newton. Therefore, 1 ATM is, I still have a number to consider. Therefore, 0.2, 1 ATM is times 1.01 times 10 raised to 5 times 2. Everything is in Newton. Therefore, this should be in Newton. You can't see what I just wrote. This is what I wrote. 0.7 ATM is 1.01 times 10 raised to 5 times 2, where the area is 2. Everything is in Newton. Now, therefore, I can write. It should be, the question is equals to 0. Why is it 0.2? 0.7 times 1.01 times 2. That was wrong. You see, that's what I said. Why I said 0.2, 0.7. You're right. I got 1.4. What did I get on the Excel? 1.414. This is my Excel calculator. I'm gonna go guess 1.4. Everything is 1.4. What was the exponent? 10 raised to 5. Then we said, I'm so sorry. I don't know if I used all the numbers properly. Let's check. Yep, correct. You happy? Now I'm gonna stop here. I said to Arnold, this thing is now, you see, question number 12 is to do with the wave. Here, it's a fluid mechanics and the wave motion. From tomorrow on, you guys will be done with Arnold and then Lucian on Friday. We're gonna finish this one. For today, I'm tired and I am done. Thank you for listening. And nobody is on the YouTube. Good invitation. Thank you for you to be with me, and without you I wouldn't have moved fast and then got also appropriate answers or correct answers, because you have been assisting me. Thank you for to be with me. I'll give you another 5 minutes if you want to discuss a specific question. Otherwise, have a good day. Okay, great. Then if you don't have habitation, the others also has been dormant. I know. AR, thank you for you to be with me. Bye guys, have a good day. Bye bye. I must go back to team.